begin by talking about the brilliance of imperfections, the brilliance of defects. So one of the reasons that I think people are particularly interested in this is the petrological information that you can extract from this particular way of looking at materials. But what I'm also conscious of is that people use luminescence of minerals in a whole different number of ways. So we can think about it in lots of different aspects. There's, for example, mineral collectors, people collecting minerals for fun or for whatever. Many of them are using luminescence as a way, or characteristic way of identifying minerals. Some luminescence is quite characteristic. Others are using it for petrological reasons, to work out aspects of the Earth history in the minerals which are encoding within their luminescence information. And I'm also aware that some, including myself and others, do spectroscopy of luminescence. And what we're doing in that is we're looking at the wavelength of light and trying to relate that back to particular defect types in minerals. And the point I would make is that if you understand not just the petrography, what the petrography is telling you, but if you understand the reason behind the luminescence, then that opens the possibility for you to interpret the petrographic meaning of luminescence far more greatly and far more deeply. And that's what I hope to be able to convey to you tonight. So luminescence has been around for a while. This is a list that we knocked up a few years ago of people identifying luminescence. Certainly, it's been known for some time that if you rub minerals in a darkened environment, they glow. Certain minerals have been known to do that. Bioluminescence, fireflies, for example, have been recorded throughout history. But one of the key issues, if you like, one of the key differences is issues related to what's been described as phosphorescence. And this is a very, very long lifetime light emitted from a material. And this was observed and reported by the chemist Robert Boyle, the Irish chemist Robert Boyle. And the way he did the experiment's quite interesting. I thought I'd share it with you. So he took off all his clothes and got into bed completely naked. And then he rubbed the stones against his body. And underneath the covers, he was thereby able to demonstrate that there was a luminescence coming from the material. And he then went on to demonstrate that that luminescence could be renewed by heating the material as well with a candle. I haven't put in a grant application to do something like this just yet, but this is clearly something that met the reviewers in the 17th century. So what is luminescence? Well, it's the emission of light from a material when it's been excited by some form of incident energy. And there are lots of ways to do that form of excitation. The ones that many people use are different. So most of the mineral collectors are using ultraviolet radiation to stimulate or to excite the material. And that is called generally photoluminescence. It's a form of photoluminescence where you're using one form of electromagnetic radiation near the visible range, and you're exploring the emission that comes back from it. But the thing I would say to you is that that's not the only way of doing it. In many ways, it's one of the more difficult ways to do it. You can excite your sample with X-rays, for example, and that's been called over the years either radioluminescence or more recently ZEOL, which stands for X-ray excited optical luminescence. And we can also irradiate the material with cathode, with electrons. We call that cathode luminescence. That is a very common petrographic technique where people irradiate the surface of polished blocks with electrons and take images of the materials the way that they are luminescing. And we've got some examples of that coming up. But there are others. There's heat thermoluminescence that is used by many people using quaternary dating, for example. Combinations of thermal and laser stimulation are called OSL. And we can also hit it with very unusual forms of excitation, such as beams of ions. And if we had much longer, then we can talk about why people would go to such extraordinary lengths to excite samples and what information that encodes. So we can hit the sample in all sorts of ways. And we really use in earth sciences just a few of these. But the point I would make is that some of the more exotic ways of exciting samples provide us with more petrological or mineralogical information potentially. So the light that's emitted, we tend to assume that it comes from the visible range, and we're hitting a sample with one form of electromagnetic radiation, perhaps UV or X-rays, and what we're finding is that we're getting visible light out. And sometimes, depending on what material, what excitation you're using, some people will spectroscopically analyze the ultraviolet for luminescence and also the infrared as well. So we're seeing some form of light emitted back from the material, and that can be seen visually in many cases, or in other cases it can be measured spectroscopically. And the general rule of thumb is that when you hit it with one form of energy and look at what comes off again, then it has to be that the photon emitted is a lower energy than that absorbed. So people ask me, what's the difference between luminescence and X-ray fluorescence? And in many ways, X-ray fluorescence does mean the emission of electromagnetic radiation. It, strictly speaking, observing light when you've hit a sample with X-rays is X-ray fluorescence. But to separate that from the technical, from the analytical method of XRF, which is looking at composition, the community has adopted the term X-ray excited optical luminescence, or ZEOL, to study the light coming off the sample when it's been hit by a form of X irradiation. So we say that fluorescence is when you hit it with one form of electromagnetic radiation, and then we get out another form of electromagnetic radiation, which has a lower energy. And the other thing that I'm going to say is that that process is essentially instantaneous. So, and what I mean by that is very variable, but I'm going to suggest that this happens in less than a microsecond. So we've got all sorts of ways of exciting samples, but what we're doing, what's common to all of these methods, is that we're analyzing the light, or leastways the radiation near to the visible range after that process of irradiation. So what I'd point out is that many people use this word fluorescence to refer to light emission following UV. And the point I would make is that that's not the sole interpretation of fluorescence. And in many ways, some of the most interesting ways of irradiating samples are not using electromagnetic radiation. They might be using electrons or other forms of incident energy. And when we use UV fluorescence or UV irradiation to look at a particular material, the point I would make to you is that we're using something with a high energy, in that case UV, and we're analyzing the visible spectrum, which has a lower energy. So you put in more energy than you're getting out. This is a feature that we're going to come back to. So many people are using UV to do that. You'll be able to buy lamps and things, for example, if you're using UV. The UV straddles quite a wide range, and it's divided into three bands, UVA, B, and C. And what we're doing here is you can buy particular bands, if you like, in a UV lamp. And many mineralogists, many collectors have a variety of UV lamps or UV tools which specialize in different parts of this spectrum. So what we're doing is we're using different wavelengths of irradiation. And the point I would make as well is that the energy of the irradiation is increasing as you go from UVA to UVC. And the energy of the incident light, or the incident electromagnetic radiation, is quite important. You get more out of your sample if you hit it with more energetic photons. Okay, so that is what's meant by the term fluorescence. And another word that you'll see sitting around is stimulation. And it's a rarer phenomenon. It is found in minerals. Many of the people in the dating community are using stimulation. And what they're doing is that they're hitting the material with a photon, which is less energetic than the actual incident radiation. So the energy that they're getting out, the photon emitted, is more energetic than the radiation they're putting on the sample. And when that happens, you don't get something for nothing. What it means is that there must be stored energy within the sample. And what you've got is essentially the energy is being added to that of the incident photon. So for example, using the UV here, so you might, for example, be measuring in the blue, which is quite high energy, but for stimulation, you would hit it with photons down in the orange or the red, which has less energy. And this is a process of stimulation. It's measuring the amount of stored energy or stored charge within the crystal. And that energy is what's been put in what is sometimes described as in energy or electron traps. And they're defects within the structure in which an electron can sit. So in other words, if I hit my sample with something in the infrared, let's say 1.3 eV, and I see a response up in the blue or in the higher energies, let's say 2.9 eV, what that means is that my mineral had charge within it of 1.6 eV. And we've somehow managed to get the mineral to combine the incident radiation with that which was stored. And this is what's called stimulation. So an example of that would be that we irradiate it with 1.3 EV photons, that's something in infrared, and then we see something much greater back in terms of energy. So what causes the material to luminesce at all? And I'm going to start with a very simple answer to that, which is that luminescence is an indicator of the presence of defects within a structure. So you've got the energy of the photon coming out of it, the lifetime, we'll talk about lifetimes in a moment, of the light coming out. These are dependent and they're clues to the exact nature of the defect in the structure. And what are defects? Well, they might be chemical defects. They might be, I'll talk some more about this in detail as we go forward, but they might be bonds, broken bonds, structural misalignments or something of that nature. And these create the luminescence in the material. And its color, the energy of the photon, and the lifetime are both clues to the exact nature of what that defect is. And as you can probably guess, it's very dependent on what mineral we're studying. What this sort of means is that perfect crystals in principle would emit very little light when they're excited. And what luminescence is doing is telling us about the imperfections, the defects that occur in all natural solids. Okay, so what do I mean by this word defect? Well, it could be some form of chemical impurity. So let's say corundum, for example, is aluminium oxide, but nature is a dirty system. We're all familiar with that. And where you grow corundum in the natural environment, it commonly grows with chromium within it, and that creates a red luminescence. And similarly, calcite, when that grows in the natural environment, in the Earth's crust, it typically picks up other divalent metals, and one of those is manganese. So these are examples of chemical impurities which are found within natural materials and which impart a characteristic luminescence. So let me give you some examples. This is an image from, this one is actually cathodoluminescence image of a zircon crystal, and it has a particularly sort of even yellow color. And here we can see that the distribution of that color is telling us something about the growth of the crystal. There's oscillatory zoning and sometimes zoning along cracks. And in this case, we know that the light is coming from tiny amounts of the element dysprosium. So this is one of the rare earth elements. And the zoning occurs because the dysprosium content in the crystal is variable across the crystal's volume. So what we can see encoded within the luminescence here is the distribution of a chemical element. Now, not all defects are chemical impurities, and indeed the majority of defects in rock-forming minerals are structural imperfections. And they might be, for example, holes where atoms should be, they're vacancies. They might be elements with the wrong charge, for example. So, for example, things such as O1 minus, where O2 minus should be, and I'll give an example of that. And they may be broken bonds where bonds don't join up, or dislocations, and many others. And indeed, people are spending many lifetimes trying to work out the exact nature of many of the defects which are behind many of the luminescence in rock-forming systems. So this is not a trivial job for us to identify what the cause is. And many people are investing many hours of academic time in trying to work out these problems. So let me give an example. There's a rock salt, for example. There is fluorescence from rock salt, and one source of that is a missing ion. It's a chloride ion we would expect to be there. The chloride ion is absent, and in its place it has trapped an electron to maintain the electronic charge, the neutral balance. And we call that an F center, and it is responsible for color. It's responsible for sometimes for bluish or purplish colors in rock salt, and it is also responsible for a bluish fluorescence from this system as well. So we see that in example from here, from rock salt, and it's also present in fluorite. So here's a fluorite crystal with a nice even blue color. And again, we think these are vacancies on the fluoride site. But as we see with many natural systems, and I've added that point here, what we often find is that there are combinations. So here we have blue color from the F center, from vacancies on the fluoride ion site. But there is also a perception that the blue color here may be coming from tiny amounts of the element europium. So there may be combinations of effects affecting luminescence in natural systems. And one particular feature that we have, for example, in feldspar, most common mineral in the Earth's crust, what we find there is a blue luminescence is present in almost all feldspars. And work that I was able to do in the 90s and in the early parts of the 2000s was able to show that the blue luminescence on this was due to a defect whereby we had an oxide 1 minus where we were expecting O2 minus. And we related that to the presence of these two aluminium sites. So in most feldspars, if I flip back, we have something called the aluminium avoidance rule. The aluminiums on the feldspar structure sit opposite each other. But if you put them next to each other, this creates overall positive charge in this, and that is offset by taking something that was 1 minus, 2 minus, and turning it into something that is 1 minus. It puts what we call an electron hole on that bridging oxygen. And we did some spectroscopic work which demonstrated that this was associated with blue luminescence in feldspars, this particular defect type. So when we see images of feldspars with these blue luminescence here, what we're able to do is to take the spectroscopy, but it's telling us about these oxide ion defects, and we relate them in turn to states of aluminium order in the feldspar. So I became interested in this phenomenon of luminescence, trying to understand the information that was encoded within feldspar luminescence. So this is a very even, unaltered feldspar, high temperature feldspar, but the vast majority of feldspars in igneous rocks and sedimentary rocks around the world have a very different luminescence. So here are some from cyanitic rocks, for example, from Greenland. And what we see here is that the center of the crystal is blue. That's the original high temperature feldspar. But around the edges and around the contacts, we can see the luminescence has been changed into this red color. And what we were able to determine from this petrographically was that the alkali feldspar crystallizes blue, but then interaction between the rock and the mineralizing fluid created a luminescence, which was red. And by understanding the exact nature of the blue center as this state of order, what we were able to demonstrate is that it was being removed and that the luminescence was altering to red. And in this way, we were able to demonstrate how alkali feldspar luminescence can be used to track the passage of mineralizing fluids through the crust. So that's a quick run through, if you like, of the big picture stuff. What's the drivers for luminescence in minerals? And now what I'd like to do is ask you guys a question. And I'd like you to imagine if we grew a crystal infinitely slowly, as perfectly as possible, would it A, grow with no defects, or B, would it grow with defects in it? So this is infinitely slowly, as perfectly as possible, would the crystal have defects? Now, I think Kevin's going to do a survey for us. So what I'd like you to do is, on the quiz that's just dropped up, decide whether you think it would grow with no defects or whether it would grow with some defects. And then when we've got the data in, what I'll do is I'll discuss that with you, see where we think that's right. I don't know if you guys can see the results, but roughly 70% said it would have defects and 30% said it wouldn't. And this is an interesting thing. I've discussed this with students and other academics, generally speaking. And the point I would make, the answer I would give you to this is that yes, it does have defects. And what I'd like to do is to explain to you why that must be true. So we know from thermodynamics that the Gibbs free energy, the driver, if you like, for thermodynamics, let me get that out of the way. There we go. This is a sum of two components. One is delta H, the enthalpy, which is essentially the energy term, if you like. But in addition to that, we've got this entropy term, T delta S, or in fact minus T delta S. And what we're doing is we're trying to minimize that delta G value, the most thermodynamically stable state. So in this system, delta H is the enthalpy, it's the energy of the system. And the way that I like to explain this to my students is that delta H is everything in its proper place. This is the very ordered world where everything is sorted. But the other contributor to this equation is entropy, and that's the disorder of the system. And what we think is that the way we understand this is the universe is naturally progressing towards more disordered states. And more to the point, disorder is multiplied, that delta S is multiplied by a T for temperature as well. So let's take those two components and think about what they mean in terms of defects. So let's imagine I have a thermodynamic function. This is delta H, and here's my defect concentration from none on the left to more on the right, and the values don't really matter. But delta H hates things in the wrong place. So as I increase defects, whether they're chemical or physical, it doesn't matter, the delta H of the system increases dramatically. So delta H is saying it doesn't want defects, it doesn't want substitutions, it likes nice, pure, perfectly crystalline solids. But delta S, or minus T delta S, they love disorder, they love shaking things about, making sure that things in structures are not quite as straightforward as we think they are. And that process of minus T delta S creates a curve which goes down the way, and it flattens off as we have more and more defects. And if we think of delta G as the sum of those two components, then it dips down initially and swings up towards the right. And what that means is that the delta G, the minimum delta G, always occurs in a material with a finite defect concentration. So if I grew a crystal infinitely slowly and at perfect equilibrium, then it is not that it would have no defects, but rather it would grow with the optimum defect concentration. So the upshot is that there is a play between those two components, but the key thing here is that the optimum defect concentration is never zero. It might be very few defects, particularly at lower temperatures. It might be many more defects, particularly at higher temperatures. And what's interesting to me when I ask that question of people, should perfect structures have defects? The thing I'd point out to you is that defects stabilize structures. And I would argue that the word defect is the problem. We kind of assume that these things are features of crystals which shouldn't be there. And what I would argue is that these things are features of crystals in all cases. They are always present. They may be more of them and they may have particular characters, but the key point to me is that all structures have defects. So it's not about whether or not there are defects. What we need to ask ourselves is what is the optimum defect character and the optimum defect concentration. Anyway, I hope that makes sense. And what the good news of that is, if you're studying luminescence, is it means that most solids, in principle, most minerals should have some luminescence of one nature or another. There are some exceptions, which we'll talk about in a moment. But what it means is that we have potentially luminescence can be an extraordinarily rich way of interrogating the defect structure of minerals and understanding precisely what information is coded within them. Okay. So let's take the next step. Let's go to understand precisely what's causing luminescence. So the first thing we need to understand is that during luminescence, we've got a process. Three things take place. The first is that the crystal absorbs whatever energy we've hit it with, that incident energy, and that typically excites electrons. And where the electron used to be becomes what we call an electron hole. The energy might transfer from one place to another, from the absorption site. And then when we get luminescence, what's happening is that the energy is recovering, it's going back to the ground state, and then it needs to deposit, it needs to emit some energy to do that, and it emits a photon of light, and that is what we call luminescence. So to understand that process more detail, we need to understand something about energies. And in any solid, all of the energies, the possible energies that an electron might have in a solid are quantized, and only specific energy levels are allowed. So I've sort of listed out, here's a theoretical solid, and here are all the possible energy levels. And we have a number of electrons. So the structure might have a certain volume of electrons, and we start filling up this structure from the bottom. And the upshot of it is that we come to a point when we've filled this structure with all the possible electrons. And now we've run out of electrons in the material. And that point at which, if you like, the material is filled up like a liquid filling up from the bottom, we call that the Fermi level. And that's called the ground state. And for many minerals, that Fermi level lies between two bands, and we call the bit in between the band gap. So that is true for the vast majority of rock-forming minerals. But for a few, and I'll talk about which ones they are, sometimes the Fermi level sits in the middle of a band. And in this case, we have a slightly different situation. That means that we could, if we had more electrons, we could have carried on filling up this band. And I'll explain what that means in the next bit. So the key thing here for me, just trying to understand this as we go on to the next stage, is what does that mean in terms of energy and how things work? So this is a summary of where we've got to in the first 40 minutes or so. So some definitions of luminescence, fluorescence stimulation. We've talked a little bit about defects. I hope you understand that defects are a feature of all solids. They are stabilizing minerals, and that's why there is such a rich spectrum of different luminescence behaviors in the mineral kingdom. And we've started to put our toe into the business of electronic models for solids. So I think I've been going for about 40 minutes, and my understanding is that that's probably when people's brains are starting to get full. So my suggestion is we take this moment, we'll take a break here, and then we'll come back to this. So we got to the point where we talked very much about the generalities of what luminescence was and the sorts of things that might be encoded in that. Let's take a look at, we sort of started to get involved in looking at the physics behind this. And the point I made is that when you see luminescence, we have to absorb energy first, create that excited electron. It moves around the mineral, moves around the structure, and then creates luminescence. So we talked about, in majority of situations, in minerals, in rock-forming minerals, we have filled up the electrons from the bottom of the possible different quantum levels, and we come to the point when all the electrons are filled up all the bands, and we call that level the Fermi level. And there is an energy gap between a band which is filled, which we'll call the topmost band or the valence band, and then the empty band above it, which I'm going to call the conduction band. And when I hit a mineral with an electron, what I'm doing is I'm promoting one of those electrons from the valence band to the conduction band. And the simplest scenario is simply that the electron is excited and it falls straight back again. And this process is what we call Rayleigh scattering. So it takes a few femtoseconds, the light's emitted, absorbed, and then it simply gives you back the same energy of photon. So that's the simplest scenario, and that's simply just you hit it with a photon of one energy, you get that same photon back again. So we have a band gap here, and if there's nothing in the band gap, then that's all that's going to happen. We just simply excite the electron and it drops straight back again. But the key thing here to bear in mind is that actually the vast majority of these types of materials, depending on the size of it, that band gap might be between, let's say, 1.5 and 3 eV. So if this process of exciting the electron falling back again is more than 3 eV, then we can't see anything. So if we have a really big band gap, something that's 7, 8 eV, then we're never going to see that simple excitation and return. We need a photon of something like 8 eV to create that, which is right the way up in the very intense ultraviolet. But in some materials, that band gap might be smaller. If the band gap is within the visible range, then we can absorb light, which is of a visible wavelength. So what do I mean by that? Well, let's imagine the band gap is quite small. Let's imagine the band gap is just, say, less than 3 eV. Then this means that something that's more than 3 eV, a photon that's more than 3 eV, like blue and violet radiation, is absorbed. That can jump across the gap. But anything that's smaller than that, anything with an energy that lies within the band gap, is simply reflected. And such minerals are going to end up with very strong colors, and they tend to be reds. So the reds are reflected, whereas the blues and the violets are absorbed. And this is the structure of minerals such as cinnabar and hematite. They have small band gaps, and they absorb high energy photons into the conduction band, but they reflect low energy photons, which corresponds to the red end of the spectrum. So that's a small band gap. And in some cases, you can have materials with no band gap at all, in which case, when you try to hit it, it will absorb any photon that you hit it with. There's no minimum energy at all. And when you end up with that, what that mineral looks like is it's essentially black. It absorbs all photons. And typically it will have a metallic luster as well. It will often have a metallic luster. So this is the electron structure of metals, for example, but it's also the electron structure of sulfide materials such as galena and things like this, or some form of other sulfides which are quite metallic in their luster. And it's because they absorb all energies and they reflect them back very, very effectively. There's no band gap there. So there is a relationship between the size of that band gap and the color of the mineral. So for things which are wide band gap here, there's basically nothing in the visible range. There's no energy levels in that visible range. So you'll see no color in these minerals and you'll see no fluorescence. And the upshot of that is that many rock-forming minerals that are transparent or white, their basic band structure is like this. They have a very large gap within them. But remember, as we said in the first lecture, this is just, if you like, the bulk structure. There are going to be defects here as well, which will modify that. In the case of minerals with small band gaps, things like cinnabar and hematite, the band gap is quite small. It means that it absorbs blue and violet radiation quite happily, but it reflects and refuses to absorb things in the red, and that gives it that red color. And if it's metallic or black, then what's happening is this band gap is now so small that it covers the entire visible spectrum. In other words, any photon of visible light will be absorbed into this conduction band. So there's a relationship between the absorption and the color, the structure of the band gap and the color, which is implicit. Now, what do defects do to this structure? So defects influence energy because they generate new bands in the material. So when you add a defect, it either bends the existing bands, moving them to a different energy, or it creates new levels within that band structure. So we know that radiation is emitted when an electron goes excited to a high level, then falls back again. But if there is a defect within that, then what that does is it introduces new energy levels into the band gap. So we said in the first instance, if this was just a pure band gap, very large band gap, the electron jumps to the conduction band and falls back again. But if we have defects, then something different happens. The energy is absorbed, it finds all of these extra levels, rolls down them, and the last bit, the last jump, is associated with a photon of light. So during luminescence, the implicit thing is the presence of the defects, which increase and introduce new energy levels into the band gap. So the absorption takes place, the energy is transferred, it finds the defects, and then a photon of light is absorbed, which corresponds to the energy between the bottom of that gap and the top of the valence band. And that's why we end up with fluorescence in minerals. It's because these defects have introduced new energy levels. So we said that the defects can be metals, they can be broken bonds, they can be vacancies, all sorts of things. What happens to defects with time? Well, you see, defects can be isolated. That's an interesting way to think about them. That's the way we tend to. But what's different between a synthetic solid and a mineral is to do with what happens over geological time. So defects can be isolated, but a defect in a structure creates a strain field around it. So here on the left, I've got two separate defects. And diffusion over the time, over geological timescales, might move these defects slowly through the structure. But if they come close to each other, as they happen, as we see here on the right, then the total strain caused by the cluster is less than the strain caused by the two individual defects. And what this means is that in minerals, what's different between a synthetic solid and a mineral? A synthetic zircon, let's say, that I've made in my lab, and a natural one that I've collected from the field. The difference lies is that natural ones have had geological timescales over which clustering of defects has occurred. It means that the defects are not isolated items, but they actually migrate and sit next to each other. That means that the properties of a natural mineral in terms of fluorescence is very different, or is often different from that of synthetic mineral analogues. Natural minerals often behave very differently to synthetic mineral analogues. And this is the reason why they don't have geological timescales over which to cluster. So, for example, here's a material I might have made in the lab, and it might have a couple of ions, one of which is big, too big for the site and causing the structure to bend upwards. And then the one on the right, the blue one, is too small. It's causing the structure to flop inwards. Over geological time, it's common for these things to migrate towards each other. And when they sit next to each other, you end up with a cluster. So this leads me on to what I hope is very important point number one, which is that defect clustering is indicative of a geological history. They're different. They mean that natural minerals are different to their synthetic analogues. And it also means that if I take a natural mineral and I treat it or heat treat it or modify it in some way, then what I'm interfering with is the history of defect clustering. And actually, this issue of defect clustering is what is used to distinguish between natural, treated, and synthetic gems, for example, in the gem kingdom. So we've said that defects form, they might be clustered, these are big issues. Let me take you through some simple nomenclature and the way that this has been evolved. So we know that certain metals introduce pretty predictable energy levels into a structure. For example, when you substitute manganese into structures, it's very common for them to have a yellow or an orangey luminescence. And this is typically a band around 580 or 600 nanometers or so. So here, for example, is an image of a calcite crystal from a mantle xenolith. And in here, the oranges and yellows that you can see are related to manganese distribution within that crystal. And we saw the picture of the zircon earlier on. What's happening here is the dysprosium is adding particular predictable energy levels into that band gap. And the final electron jump at the bottom can be predicted to be around about 580 nanometers. And that's why, again, we have these very, very predictable additions. And you can see, for example, here, this is a natural fluorite from the open literature. And what we're observing are rare earth emission lines throughout the spectrum, giving these particular zones. And where we have a substitution of a metal, which introduces a series of very predictable energy levels into the band gap, we call that an activation. So we say that a particular ion activates the luminescence. So what's happening is that the activator is adding that predictable series of energy bands so that when the emission takes place, it rattles through all of these levels, and at the end of the day, it drops that, and that photon of light that comes off has a particular energy. And for the case of manganese, for example, that is in the yellows or sometimes in the oranges. So the exact wavelength of the emission is roughly in the same place. But in detail, it can move depending on the coordination state of the metal. So the energy levels are broadly predictable, but not precisely predictable. And that's really helpful for us because, for example, in this image of a sedimentary rock, it contains both dolomite and calcite, and both of them are being activated by the presence of manganese too. But we're able to distinguish between them because the coordination state of the manganese is different in these minerals. And that causes the energy level to shift just slightly. It means that we end up with a situation whereby you can distinguish between the minerals and you can interpret them petrographically in these sedimentary rocks. So we have activation, which is the introduction of a series of bands which sit in the band gap with a broadly predictable structure. But some metals introduce so many energy levels that there is never actually any jump at the end of it. And so, for example, if you have iron in a structure, particularly if it is a hybrid oxidation state between 2 and 3, then it adds so many new bands to the band gap that essentially there's no luminescence. And we call that quenching. That's the term that's applied to it. We say that where a particular ion is present in a structure, we don't see any luminescence. And that's described as the quenching. And what that means in electronic terms is that we have the defect here in these black lines, but the quenching ion has added so many extra bands that at the end of the day, there's no final photon emitted. So there is absorption, energy rattles down through the manganese, but then it finds its way back to the valence band without ever having gone through the process of emitting a photon. So some metals, and the most common one is iron, particularly if you have a combination of iron 2 and iron 3, they essentially kill off all of the luminescence. Okay, so we have quenching elements, we have activating elements, we also have what are known as sensitizers. And this is related to something called the quantum efficiency of the process. So we've talked about very simply about irradiating a crystal with energy and seeing some of that energy being transferred across. But in reality, there is an extraordinary amount of energy loss in this process. It is not particularly efficient. And estimates typically suggest that something like 99.5% of the energy is lost to thermal vibrations in this process. So the amount of energy that's deposited on a sample and then goes on to provide us with fluorescence or luminescence is called the quantum efficiency. And what's happening with quenchers is that they're particularly effective at absorbing energy, and the same is often true for sensitizers as well. So they are ions on a structure which really improve the quantum efficiency absorbance of absorbing the energy in the first place. And some sensitizers, they improve the quantum efficiency of energy transfer. So those particular ions are called sensitizers. So here, for example, this is fluorescence of a mineral willemite, which is a zinc silicate. And the yellow that you're seeing here is actually, the green that you're seeing here is, again, its presence to do with manganese. But actually the sensitizer here is the presence, so it is the presence of some degree of this manganese here. So you've got a little bit of zinc and you've also got manganese as well. That improves the luminescence. So many of these luminescent centers are modified by the structure around them. That's the key thing. So if you wanted just Noddy's terms for these things, then we can talk about the process of activators. If an ion is present in a structure, it will create luminescence. A quencher, which extinguishes luminescence if it's present in a material. And then also, and this is more difficult to constrain, but sensitizers, which improve the quantum efficiencies of processes which are otherwise active. So we can sort of draw a diagram of this, which sort of brings it all together, sensitizers and activators. So the upshot of all this is that when we look at the luminescence of minerals, and here are some images that I picked up from the literature, all of these processes are combinations of interactions between defect types, metals, quenchers, and sensitizing. So the common ions which are activators tend to be things like manganese. Rare earths are very common, dysprosium, europium. iron 3, if there's no iron 2 present, iron 3 can fluoresce as well. Any slight hint of iron 2 present as well turns iron into a quencher. So anything with a mixed valence actually is a very, very efficient quencher. And in the Earth system, that's typically iron 2 to iron 3. So we can talk about all of these different ways of thinking about it, and we can break it down into simple terms. Okay. So let's go back to the physics behind this, the funding of interactions. So fluorescence is a very fast emission, which comes from an electron going through the process that we did the little cartoon for. So we have lots of different photon-electron interactions. The electron is excited, it absorbs the photon, it may drop back, it may emit the photon, or sometimes you might have the combination of locked energy with the photon to create stimulation. So we end up with all sorts of possible things going on in the structure. Let's take the simplest of those, which is simply Rayleigh light scattering. And let's think about the lifetimes of this process. So the absorbance of energy, if I hit my sample with a photon of, let's say, UV, that process is very, very fast. That takes femtoseconds, 10 to the minus 15 seconds. So the absorption process is essentially immediate. And if we have the light just given straight back to us, same photon energy, that's called Rayleigh scattering, that occurs also in femtosecond timeframes. So the process of absorbing energy is very, very quick, almost immeasurably quick. But in luminescence, what happens is the energy is absorbed, then it is transmitted through the structure, and then it goes to another energy level. Now, when an electron absorbs energy, I've expressed it up to now really just in an electronic sense. The electron jumps from one level to the next. But there is a consequence to this as well, which is that the crystal becomes excited and the atoms very, very slightly move. And this movement happens typically on the picosecond to nanosecond lifetimes. So the absorbance is 10 to the minus 15 seconds. And then what is, in terms of the electron, the excited state of the electron, 6 orders of magnitude later, the crystal might relax slightly because the electron is excited. And what that means is that sometimes a structure will physically change. The atoms will move closer and the energy states will change. And that's happening on 10 to the minus 12 to 10 to the minus 9 nanoseconds in time. And what this means is that when you get the photon of energy back, on this time scale, it's not the same as the crystal that absorbed it. So the crystal has actually relaxed between absorbing the energy and giving you the electron back. And what that means is that the energy profile of the initial state and the absorbed state are not the same. And what this graph is trying to show you here on the right, it's called the Frank-Condon graph, is it's trying to demonstrate that when you absorb energy here in red, it goes to a series of electron bands higher in the structure. The movement of the atom means that this structure isn't quite the same as the one that it starts off with. It means that when we hit it with absorption, the energy we get back is always slightly less. And that's because the crystal that's emitting the energy back is not quite the same crystal as the one that absorbed the energy. And a certain amount of energy is lost in moving the atoms just slightly. So the light coming back to you is typically hundreds of picoseconds or hundreds of nanoseconds after the absorption. And that leads me on to what is a very important point, which is the emission of the light is from the excited state of the atom, and the energy is lost in slightly rearranging the atoms as they become excited. And that is called the Stokes shift. It means that when I get the energy back again from the photon, it's always slightly less than the energy that I put in. So the absorption is essentially instantaneous in femtosecond times. But if you leave the crystal excited for, let's say, a nanosecond, then the crystal will relax slightly. And then the photon you get back is not from the same material as the one that absorbed it. The crystal is rearranging itself slightly. And what that means is that the absorption and emission are not 100% efficient. The energy is lost in rearranging the structure in response to the excitation. And that lost energy means that the energy you get back is less. And this difference, if you like, you don't get something for nothing, is called the Stokes shift. It means if I excite the sample with high energy photons, I will end up with getting something back with lower energy. And that leads me on to very important point number 2, which is that the crystals are not at 0 Kelvin, and that means that the lattice is actually vibrating. And those lattice vibrations also interact with the structure. They rob it, if you like, of some of the energy. And the upshot of that is that when you put energy into something, perhaps if you hit it with UV, the energy you get back is always less. The crystal has stolen some of the energy when you get it back. So we said this process is about 100 nanoseconds. And what's interesting is you can measure the lifetime of the luminescence. And some things speed luminescence up and other things slow it down. Let's think a little bit about things that slow luminescence down. So if the place where the energy is absorbed and the place where the energy is emitted are physically far apart in the crystal, then the energy has to travel from one part of it to the other. And if that happens, then the energy requires a finite amount of time to get from one place to another. So the fact that the energy has to move through the structure slows it down. And people have attempted to measure this. And again, it's different for different minerals, but certainly it's in the nanosecond to microsecond lifetime. So the energy has to travel around. The other thing is that electrons have spins. You can have an upspin or a downspin. And some electron jumps can only take place if the electron flips its spin halfway through, and that's not allowed. That's called spin forbidden. And to do this, what happens is that the energy has to go to somewhere else, have its spin inverted, and then come back again, and then it can make the electron jump. So that process of flipping its spin slows the electron down again, slows the luminescence down. So things with spin forbidden transitions, these are typically the transition metals. And what that means is that when I measure the lifetime of transition metals, they tend to be in a much different scale. So that manganese, for example, again, it depends on the mineral, but it's typically about 2 milliseconds or so. Iron is a millisecond, praseodymium is microseconds. And remember that the natural lifetimes, if we weren't mucking about with the spins, would be something in the nanosecond range. So these are being delayed by orders of magnitude. And the other point I'd make to you as well is that if you're delaying the luminescence, you're interfering and reducing its quantum efficiency. So in spin-forbidden transitions like this one, what's happening is that the transition is so slow because the energy has to go on holiday to another part of the crystal. It has to have its spin flipped over, and then it has to come back with the spin flipped. And that energy, if you like, that third place where the energy is residing is called a triplet state. So we talk about not just the absorption of the irradiated photon, transference of the energy through the structure. In some cases, the energy then has to go to a triplet state somewhere else and then come back again before the luminescence can take place. And that process, the physicists call that phosphorescence, whereas we mineralogists tend to call that just slow fluorescence. Phosphorescence is a term we tend to use for things which are slow in the second range. So spin forbidden delays tell us that the energy, once it's deposited on the structure, has to go through a whole series of different places, and it's modified and changed, and it comes back to where it started from. So all of this is expressed in these quite complicated diagrams, the Jablonski diagrams. What they're demonstrating is that energy jumps across the band gap. Sometimes it goes to a triplet state over here. Sometimes the energy goes back and then is reduced. Sometimes the energy relaxes from the triplet state directly. You don't have to worry about this. But the upshot of it is that many of the transition metals have very, very low, very long lifetimes. They have lifetimes in the millisecond to microsecond, and they have low quantum efficiencies. All that energy jumping about from one place to another is a recipe for the luminescence to get lost. And as you've gathered here, the distance that the energy has to move through the structure from one defect to another is strongly influenced by defect clustering. So if we have the triplet state physically right next to the recombination site, like the iron, the manganese, let's say, then that process happens much more quickly than if these things are physically separated in space. So with minerals, where we have geological timescales creating optimized defect clusters, this process tends to be quite fast, or certainly much faster than in synthetic mineral analogues. So the key thing that I'd point out to you is that the lifetime of the luminescence gives you an indication of the source as well as the color and the wavelength. So we've said that manganese often emits as a broad band around about 580, 600, but also what is characteristic about it is that its lifetime is typically very slow, typically in the millisecond range. And many of these transition metal related activations are these very slow for spin forbidden transitions. And if you think something is an activation is an activation process, then you can test that by measuring the lifetime. So things like that slow luminescence down, and let's think about things that speed luminescence up. So let's imagine that you've clustered. Well, first of all, let's take just an analogy. Let's take a bucket with a hole in it. And let's imagine that you fill the bucket and you wait for that bucket to empty, and you measure how long it takes the material, the bucket to empty all the water out. And let's say it takes a second, something like that. Very quick. Now, sometimes if you can see the hole at the front, you can see the water gushing out. But let's imagine that what I've done is I've brought this defect up against another defect with a much faster lifetime. So let's imagine that the bucket has got a hole at the front that I can see, but let's also imagine it's got a hole at the back that I can't. That means if it took me, let's say, a second to measure for this bucket quickly to empty, if it's got a hole at the back, it will empty much more quickly. What this means is that we think that natural lifetimes are typically in the 10 to hundreds of nanoseconds range, but when we measure some luminescence in minerals, we find that they're much faster than that. They're even faster than that. And we call that Dexter resonance. What that means is we can't see the hole in the bucket. There's a hole in the bucket we can't see. In other words, there is some form of energy loss mechanism taking place, which is not giving luminescence, but it's robbing the site of its energy more quickly than the luminescence we expect. So the apparent lifetime is shorter because the bucket empties faster. Now let me show you an example of this. And this is from experiments we've done using X-rays. And we've used focused X-rays on a series of quartz crystals. And we're measuring the lifetimes of different parts of the process. And what we demonstrate here is that sometimes these things are very, very fast. So in this very bright grain here, marked A, for example, the luminescence is over and done in picoseconds, hundreds of picoseconds. Whereas in this grain here, which is much dimmer, the luminescence is taking place in nanoseconds. So we find as we look around different crystals that the lifetimes of each of these are different. And we explain that in terms of different degrees of defect clustering. Okay, so we said that that can accelerate things, and it's essentially telling us about defect clustering. If I put two defects physically close to each other, they can interact with each other. If they're far away, then they are essentially independent. And the same is true of this type of relationship. So let's imagine we've got electron structure of one material, one defect here on the left, which I've called the donor, and I've got another material over here, which I've called the acceptor, and the luminescence is coming from essentially this acceptor side. If I put them far apart, they don't interact, but if I put them together, then these things effectively become a single series of energy. Energy can flip between the electrons between them. And that means that the luminescence happens much more quickly than we expect. So we can talk about things that slows luminescence down, these spin-forbidden transitions, moving electrons through structures. Things that accelerate it are defect clustering, physically putting defects close to each other such that the energy transfers between them much more effectively. And the thing I'd point to you is that this is in turn indicative of the geological and thermal history of the rock or mineral that you're studying. So how do we measure these things? Well, this is an example of X-ray luminescence, for example. What we've got here is a simple decay. Here's the pulse. The absorption is essentially immediate in femtoseconds, but the decay has a measurable exponential decay, which I can fit and provide it with a lifetime. And I can do that, for example, here, this is plush feldspar. This is a colorless feldspar here. And this has got some bands here. This is the lifetime component, and this is the wavelength component. So what you're looking at in this graph on this side is the wavelength of the emission, and what you're looking at here on this side of it is the decay times of the emissions. And this is a colorless feldspar, and this is a colored feldspar as well. And what we see is that we've introduced a whole series of new emission bands with very, very fast decay times that fill up the middle of this graph. So these are emitting around about in the blue to the yellow, 400, 500, up here in the red, 650. And I can characterize each of these different emissions by its own wavelength and also its own lifetime. And we characterize the lifetime as Tor, and it's effectively a measure of that exponential decay. So some luminescent centers, when we measure luminescence in minerals, what we find is that they can be calculated and we can fit those decay profiles in terms of lifetimes. And what we find often is that there are different lifetimes for the same center. So here, for example, this is a decay profile from X-ray excited luminescence. And we find it has one component, Tor1, with a lifetime of 0.32 nanoseconds. That's very fast. And we can fit it with a longer lifetime at 1.15 nanoseconds as well. How do we interpret the same luminescence as having different lifetimes? We think that this is examples of where the defect is clustered, giving us faster responses, and where the defect is actually separated and isolated, giving us longer defect clusters. So the upshot of all of this physics is that we can use the lifetime to tell us about the luminescence in materials, in minerals. Each transition of an activator, for example, has its own characteristic wavelength and its own characteristic lifetime. So, for example, manganese is typically around about 580, 600 nanometers with a lifetime of typically 2 microseconds, something of that order. So if I think that manganese is involved in my response, I can use that information to tell me whether manganese is indeed a response, is indeed the source. But what's really important is that lifetime is very, very sensitive to variations in what I've called the electronic environment. And that is really probing the local coordination, not just of the activator, but also it's telling you something about how defects are clustered. And this is giving you information, not just about the chemical history of the rock, the geological history, it's telling you about the thermal history as well. And lifetime is sensitive as well to these quenching mechanisms. Sometimes quenching can reduce lifetimes. So this is the end of the lecture, and I hope that it's been of interest to you. We've done a huge amount of information. One is that we've got fluorescence as how fluorescence works. The thing I would say to you is that fluorescence is a very, very subtle and very sensitive probe of defects in materials, and it can give us responses of defects which are in parts per billion concentrations. That might be a physical defect, a broken bond, or it might be luminescence from a particular metal. And when we study it in detail, when we study its lifetime, when we analyze its luminescence spectroscopically, we can show how it is dependent on the local atomic environment, as well as just the nature of the defect. And the key thing is that lifetimes give us insights into defect clustering. And the final thing I'd say to you is that we can interpret this to tell us a huge amount of geological information. If we understand what the nature of these defects are, how they form, and the geological history they encode, then we can actually do some very, very sophisticated and very, very simple analysis and very simple, very sophisticated reconstructions of geological and radiation history. Thank you for your attention.
Brilliant. Thank you so much, Adrian. That was excellent. Well, great. Okay. So we have a little bit of time and we have some questions already in the chat. Steve, would you like to read out your question or like to ask your question, or I'm happy to ask it on your behalf? Just unmute yourself.
Okay, my question was, would you consider that the exposure of minerals to light results in a form of weathering?
Oh, that's an interesting way of thinking of it. Yeah, well, it certainly modifies the material. So we know that repeated irradiation particularly by UV radiation in the sunlight, changes mineral structure. Is it weathering? Depends what you mean by weathering. I think most of my colleagues would argue that weathering is a chemical change causing secondary surface-related minerals rather than a physical modification. But it is certainly true that materials which have been on the Earth's surface, for example, for a long time, so the surfaces of boulders, their physical structure is modified by repeated irradiation. And in some cases, that irradiation can create clusters, it can disperse clusters as well. Does that answer your question?
Yes.
Super, thank you.
Great, thank you. Vali, would you like to answer your question? Ask your question even?
So my question is like, can mineral luminescence used for exploration purposes like critical minerals or gemstones or any other minerals which can be identified using this property?
Yes, the simple answer to that is yes. So I became interested in the information encoded in luminescence behavior, particularly in common minerals like feldspars, to track the passage of fluids moving through the Earth's crust. And some of the work that I did in the 90s and the noughties showed how feldspar luminescence was related to temperature of formation, states of order. And that made sense of what we were seeing petrographically in thin sections, which was that red luminescence was associated with low temperature feldspars, and blue luminescence seemed to be associated with high temperature ones. So you can use that to track luminescence through the crust. Some of my colleagues, I'm aware, are using the luminescence of apatite, for example. Apatite is activated by lanthanides to track the presence of rare earth-bearing fluids through the crust. So it is being used for that. And also gemstones. Yes, there is a big field of studying the fluorescence of gemstones. And what we're particularly looking at here is to try and identify whether minerals, first of all, provenance, where do they come from? Have they been treated? And are they synthetic? So synthetic versus natural. And as I've said, tried to explain in the lecture, the thing that's really different about a mineral as opposed to a synthetic solid is the degree of defect coupling. And if you heat something, if you give it a heat treatment, it completely ruins that defect coupling. All the lifetimes change. And that can sometimes be used to retrospectively, forensically work out that gems have been treated. Does that answer your question?
Yes, thank you.
Super, Valley. Thank you.
Lovely, thank you. Andrew, got your question? I'm happy to call it out as you prefer.
Sure. Thanks very much for an excellent presentation. My question was, what might be the cause of long-lived phosphorescence on the order of minutes in a mineral following the cessation of electron irradiation?
Yeah, so there are many mineral systems, and I'm sure you're talking about things like diamonds and other minerals, which have phosphorescence. And if you go to the cinema, for example, and the lights go out, you can still see the sign which says exit here or something like that. And what's happening there are different ways to interpret that. But one of them, the most common way to interpret it, is it's actually thermoluminescence. So what's happening is you're storing charge. When you irradiate the crystal, you store charge within it. And then the room temperature is sufficient to allow that charge to be thermally activated. So as time goes on, the room temperature is kicking electrons out of the traps. So there are forms of thermoluminescence where you heat a crystal up and it glows at a particular temperature. It suddenly gives a burst of light. What we've got in these phosphorescent materials is something which is where that sort of heating process is very close to room temperature. So if you were to heat it up to, say, 20 or 30 degrees, it would give out light. So when you're holding it at room temperature, 20, 25, it is emitting light, it is thermally emitting light, but it's very close to that thermoluminescence temperature. Does that explain things sufficiently?
Sure, that's good for now. Thank you.
Great. Okay.
Super, thank you. Is it Akash? Would you like to ask your question? Apologies if I've butchered your name pronunciation.
Yes, thank you. Thank you very much for the lecture. I learned a lot. And my question would be, does the orientation of the mineral influence the luminescence properties of it, particularly when I'm doing a cathode luminescence spectroscopy?
Yeah, and the simple answer to that is yes. So we know that low symmetry solids, and I'm particularly thinking of feldspars, have a very orientation dependent response. So again, we did work with this on the 2000s, where we took single crystals and rotated them and looked at the luminescence spectroscopy in different orientations. It was very different. And if you wanted to be sure of that, then a simple test of this truth, if you like, is that if you see a twinned feldspar and the luminescence is and the material is twinning and it is fluorescent, you'll be able to see the twin in the fluorescence. And that's because the crystal is emitting more brightly in certain orientations. So if you have, for example, an albite twin, In luminescence, you can often see the twinning, and that's because the light is coming off more brightly in some directions than others. So the twin is visible in the luminescence.
Thank you very much.
Right. Are there any other questions for Adrian? And you just pop your hand up or just call out. Oh, Vali, another question. I can answer that in the chat, Vali. Any other questions for Adrian?
Okay, I think everyone's probably, their brains are quite full after this, but just as a general sort of announcement to everybody, if you're interested, if I've incited you about luminescence and you're interested to know more about it, you've got my contact details. I'm very happy to answer specific questions if you drop me a line. And yes, the emission is polarized, Fernando.
Thank you. That's quite interesting too.
Yeah, so as well as being orientation dependent, the emission is polarized. So you can do fluorescence work rotating a polarizing filter, and you get slightly different responses depending on the orientation of the crystal with respect to the filter.
And also the decay time is polarized.
Sorry, can you say that again?
The lifetime is also polarized. Or...
Yeah, that's so yes. So when we do experiments to study orientation and polarization, we use a form of excitation which is very, very high energy, which is essentially depositing energy in an anisotropic way. So where we've done these types of experiments, we've usually radiated either with X-rays or with ion beams. And the purpose of this is you're depositing energy in a way which has no polarization. But if I were to irradiate a crystal with, let's say, UV, then yes, the absorption of the light is polarized, and then the transport and then the emission of the light is also polarized as well. And in some cases, there's a rotation of the plane of polarization associated with that process. So depending on how you excite the crystal, if it is with UV, for example, then yes, that is polarized. And if it is, but if you hit it with something very, very high energy, such as an X-ray, in principle, X-rays are polarized, and we did work with synchrotron X-rays, but in most X-ray generators, they're not polarized. And therefore, you can do that to study the polarization of the emission alone. Does that make sense?
Yeah, thank you.
One more question in the chat, Adrian. How to distinguish electron beam induced defects from natural defects in the crystal? It's a good question.
This is a really fundamental question, and the answer to that is it's really difficult. So if you use high energy excitation, then you modify the material. So I talked about lots of different ways to excite the sample. I tend to use X-rays because they are not polarized. My source is not polarized, so it solves that problem. And they're very high energy, which means that even if there are just a few defects, I get a nice strong signal back. But you're quite right that if I hit it with a very high energy excitation, I can break bonds in the material. I can create defects which weren't there in the first place. And that process, sometimes what we do is we actually deliberately irradiate with high energy, and we analyze the material as a function of time. We monitor the spectrum during the irradiation, and we see if it's changing. And we do. We find examples of where the material is modifying. And the form of excitation you've mentioned there, electron beams, they are notoriously bad for modifying the sample. And that is because the electrons only penetrate something like 100 nanometers into the surface of the mineral. So if you think of you accelerating with, let's say, 15 kilo-electron volt electrons, and they stop within 100 nanometers, the volume that you've created, the energy deposition in that top 100 nanometers is absolutely phenomenal. And it is sufficient in some cases almost to amorphize the structure. So the comment that you've made there, Christian, is really, really important. sometimes when you analyze the material, you might be creating defects. And the solution is to do low energy excitation, such as photoluminescence, UV. You're only hitting it with perhaps 3.5, 4 eV photons, and this is less likely to create substantial damage to the structure. So often we're comparing low energy excitation with high energy excitation to crack this problem. Does that answer your question?
Hopefully, yes. Yes,
Super.
great.
Thanks.
Okay, last call for questions in the chat, or put your hand up or call it out. Okie dokes. I think, Adrian, we're going to leave it there. That was genuinely brilliant. Absolutely.
Super.
That was brilliant. Thank you very much.
So super. Thanks everyone for coming along.
Yeah, no, thanks. And thanks everyone for staying as well. It was a bit of a longer one today, but certainly worth it. And if anyone you know is interested, it'll all be up on YouTube in a couple of weeks.